Hello everyone, and today we're going to be talking about algorithms in RN. How can we do optimization in RN, and how can we solve these problems? So to start off with, we're going to talk about our problem. So we're going to go back to the scalar case because it's much easier to think about. So we're going to have some mapping, f of x, which is going to be going from r to r. So we're putting in a single value and getting out a single value. And what we're going to try to do is we're going to try to maximize this value. So maximize f of x with respect to x. So oftentimes what you'll see is something that kind of looks like this, if you were to draw it out. Kind of have these sloping curves. And what we're trying to do is find this global maximum point here. So there's going to be gradient best methods, and these rely on the actual computing the gradient of the function that we have. So the first order methods use the Jacobian or the gradient, depending on if you have a mapping from Rn to R or a mapping from Rn to M. Remember, the Jacobian is the more general case, the gradient is kind of the shorthand for the scalar value function. There are also second order methods that use the Hessian. We're not going to be talking about any second order methods today. There's also things called local search methods. And then there's things like genetic algorithms that we're not really going to cover in this course. They're used in robotics, but not really the canonical things that you learn initially. So the first thing we're going to be talking about is the gradient-based methods. As you can probably guess from the name, gradient-based methods use the gradient of the current parameter set to figure out what the correct thing to do. And what we're going to be doing is taking a step in the direction of the negative gradient. So if you're thinking about it in a single variable case, we have our value like this, and I take some point here, I compute the gradient, and I'm going to take a step in this direction. And I'm going to do the same thing, and I'm just going to keep doing this until I reach some point where the gradient is very close to 0. And that means that I've reached something that represents a critical point, so hopefully this is a min or a max. So there's a couple important questions when it comes to gradient descent methods, like how am I going to choose my direction? There are higher order algorithms that use more than just the gradient to figure out what the direction to take a step in, or assume that potentially your gradient is a little bit noisy in the local area. There are questions for how far a step I should take. So remember, if I'm doing my optimization problem like this, if I take a very large step, there's a good chance I'll end up on the other side. But I don't really know what the space looks like a priori. So I have to be a little bit clever about how I choose this step size, and also when to stop the optimization. Maybe you're doing some landscape that looks very, very flat, and it's fine as long as you're anywhere in this region. So you don't want to be taking gradient steps here forever and ever and ever. So how we stop the algorithms are a big question. So when we talk about gradient descent, this is kind of what the canonical equation looks like. So we have some vector set x, and we have our previous vectors, and we're going to take a step in the direction of the negative gradient of f, where that step size is determined by this parameter gamma. So we figure out what our gradient is, we take a small step in that direction, and the next value should be better. So if we look at the actual algorithm for gradient descent, I start off with some x, which is my initial x, and then what I'm going to do is, while my gradient is greater than some epsilon, so some small value, I'm going to continuously update my input vector based on the gradient. This is the same idea as I have some slope, and I'm slowly taking steps in that direction. The important properties of gradient descent is that it will converge to a local minimum in finite time, assuming you use correctly sized steps. So if you use very large steps, there's a really good chance that you'll blow up. You can't use too small steps. So gradient descent is really nice, and it works very well. But you're probably asking the question is, oftentimes in robotics, we have f of x, but we don't necessarily have f prime of x. We cannot compute the gradient with respect to some function because sometimes we're approximating it with something and we're not exactly sure about our approximation. So it would just be nicer if we could use the function that we currently have and not be required to calculate the gradient. So this gives rise to methods called local search methods. And what they do is they use samples of f of x, or evaluate, so our function, in a local neighborhood, and they're typically characterized by how you choose your different neighbors. And what that means is I have some value here. What I'm going to do is I'm going to look at x's that are pretty close. So my x t plus 1, my x of t, remember the norm is less than some delta, and I'm going to look at things that are in a local neighborhood to where I am currently. And how we choose this neighborhood is the important part of these algorithms. And also, how do we pick what neighborhood we want to move to? So the first thing we're going to be talking about is this thing called randomized hill climbing. So what we're going to do is we're going to take samples in our local neighborhood around x of t, and you can do this pretty much however you'd like, but usually this is kind of deterministically sampled based on some a priori scheme that uses some knowledge about the problem. And then we're going to figure out the objective function of each value, and then we're going to move to the neighbor with the best value. So an example of what that would look like in the 2D case. So let's say I start here, and what I'm trying to do is find the maximum. So I'm going to sample a neighbor here and here. I'm going to pick this neighbor because it's higher. And now I'm here, and I'm going to do the same thing, pick the higher neighbor, and I will keep moving in this direction until I reach the top. But depending on how I select my neighbors, as long as the size isn't decreasing, I won't necessarily reach the top exactly like I would with gradient descent, because it's not based on the magnitude. It's just this static neighborhood calculation. There's ways you can get around this, but typically this is the way it's formulated. So there are some important problems when it comes to randomized hill climbing. So let's say in this example, I'm trying to calculate the minimum. So trying to find the min. As we see here, this is the global min I would like to find. But since I'm starting here, what I'll do is I'll pick a neighbor here and here, and I'll pick this one, and I'll pick a neighbor again and again and again, and what I'm going to end up with is stuck in this local minima. So this is a problem with randomized hill climbing. You very often get stuck in local minima, especially in a very multimodal space, which means that there's lots of local minima. There are ways around this that give rise to the next algorithm we will talk about. So some important properties of randomized hill climbing is that there's no guaranteed convergence, but usually it works pretty well. They are easily stuck in local minima, and it heavily depends on your hyperparameters. How you choose those neighbors depends on your space a lot, and it's very hard to figure it out. So the algorithm I alluded to was simulated annealing. And what simulated annealing does is exactly like randomized hill climbing, but now we have a probability to pick a bad action. So if you remember, if I was stuck in this issue where I was trying to find the maximum, and there's two of them, and I start in this location. So I have a choice between this neighbor, and let's say that my probability triggers, and I end up going in this direction, and then I go back up, and then I go back down, I go back up, and I go back down, and eventually I figure out that I can go up this hill. This is something that would never happen with randomized hill climbing, because there's no way you could get out of that. It will never take a step in the wrong direction, but simulated annealing will. And what it tends to do is you decrease the probability of taking a bad step over time, so that eventually you'll essentially maximize what you currently have rather than trying to find or continue exploring. The algorithm for simulated annealing can be shown below. So we have some f, which is our objective function. We have some gamma between 0 and 1. This represents how we're changing our temperature. And then we have t, which represents our temperature. So we start off with some initial parameter values, and we'll go for some maximum number of iterations so that it doesn't go on forever and ever. Then we're going to sample a uniform random variable between 0 and 1. And if that is greater than t, our temperature, we will pick a random neighbor. Otherwise, we will use the knowledge that we have and pick the best neighbor. And then by taking gamma, since it's less than 1, and multiplying it by tau, which is our temperature decreases over time. So this allows us to escape some local minima and potentially avoid some of the problems that we saw with randomized hill climbing. So as we can see here, we have the exact same problem. So there's a probability that given simulated annealing, we will actually go down to here and get stuck just like we did with randomized hill climbing, because remember, we're taking the min. But there's also a chance, unlike we had before, that we could end up figuring out that the best direction is this way and going here. And this is done by just taking randomized actions that are potentially negative in local context. So the important thing to remember with this lecture is that each algorithm has its own niche and what it focuses on and what it's good for. Gradient descent is really good for provable conversions and when you can compute the gradient. It will almost always beat out randomized hill climbing because it'll be able to figure out the exact direction to move rather than guessing based on some neighborhood. But it can still get stuck in local minima. Simulated annealing is a really great algorithm that's used by roboracing for this exact reason. Because they're planning in a very multimodal space, even if you don't get the best solution, as long as you get a pretty good solution, you'll be better off than you were with any of the other algorithms. The other thing to remember is that in highly multimodal spaces, there are lots of local optima, and these are just difficult optimization problems. There's not really a solution to them. It's more about just managing what you can do and doing the best that you can.